Okay, now let's have a look at topic 12 of Introduction to Geometry, Circles and Angles. We'll divide this topic into two parts. Today, the first part, we'll talk about the concept of inscribed angles, and in our next lesson, we'll talk about part B, concepts related to angles inside and outside circles, tangents, and some more related problems. Okay, first, let's have a look at the concept of inscribed angles. So suppose we have a circle here, points P, Q, R are on that circle. We say that angle PQR is inscribed in arc PR in the diagram above because its vertex is on the circumference of the circle and its sides hit the circle at point P and R. Actually, the inscribed angles are enormously useful tools in geometry. In this lesson, we'll explore how inscribed angles are related to the arcs they cut off. So now let's consider an introductory example here. When an inscribed angle cuts off a 180-degree arc, we say that it is inscribed in a semicircle. The question is such an angle necessarily a right angle? So I'll give you 3 minutes to think about this question, and then I'll lead you through the solution, okay? Okay, any ideas? Alright, so we can make use of some isosceles triangles, right? So first of all, in triangle OBC, we know angle OBC equals angle OCB because it's an isosceles triangle, which is 1/2 of 180 degrees minus 50 degrees, right? So that's 65 degrees. Okay, we know this angle here is 65 degrees. And if you can find this angle here, then you can solve angle ABC, right? Also, we can make use of isosceles triangle OAB. Because OA equals OB, we have angle OBA equals angle OAB, which is 1/2 of 180 degrees minus 130 degrees, and this gives us 25 degrees, right? Since here this angle is 25 degrees. Therefore, we know angle ABC equals angle OBC minus angle OBA, which is 65 degrees minus 25 degrees equals 40 degrees, right? So angle ABC equals 40 degrees. Did you get it? So can you observe any pattern here? So you know that any angle inscribed in a semicircle is a right angle, which means if you consider this arc here, the angle inscribed in this semicircle is 90 degrees, which is 1/2 of this circle here, right? 90 degrees is 1/2 of 180 degrees. And if you consider this angle, if you consider this arc here, the angle inscribed this arc is here. This angle we have just calculated. This angle is 40 degrees, and it's 1/2 of the central angle here, right? Is that a coincidence, or is this angle always half of the central angle here? So let's try to prove that. So consider another question. Can you prove that if angle XYZ is inscribed in a circle such that the center of the circle O is inside triangle XYZ, then XYZ equals half of the arc XZ. Of course, XZ here is in degree measurement, not the length of XZ, but this is a corresponding degree measurement of the central angle. All right. So let's suppose X is here, Y is here, Z is here. So if you consider the arc here XZ, can you prove that this angle is always half of this central angle here? So we might use our specific cases previously as a guide, right? And we connect already to X, Y, and Z to form isosceles triangles. We don't know any angles this time, so we'll have to use variables to denote these angles. Since we know we want to use our isosceles triangles, we could let angle OYX equals X, and let angle OYZ equals Z, so that angle XYZ equals X plus Z, right? And isosceles triangles XOY and ZOY tells us that angle OXY also equals X, and angle OZY equals Z, right? Therefore, we have angle XOY equals 180 degrees minus 2x from triangle OXY, and angle ZOY equals 180 degrees minus 2z, right, from triangle OZY. We can now find angle XOZ in terms of x and z. So angle XOZ equals, we know this is 360 degrees, right? So that's 360 degrees minus angle XOY minus angle YOZ, and this gives us 2x plus 2z, which is twice of x plus z, right? So this is 2x plus z here. Therefore, we have proved the arc xz equals 2x plus z, which is twice of the angle xyz, right? Therefore, we have angle xyz equals 1/2 of the arc xz. So this angle here is always half of this angle here, the corresponding 1/2 of the corresponding central angle. Did you get it? Again, this is another important property of the inscribed angle. So let's make a summary here. So the measure of an inscribed angle is 1/2 of the measure of the arc it intercepts. For example, if we have a setup here, OPQR, O is center of the circle, PRQ are the points on that circle, we always have angle PQR is half of this angle here, POR, or half of the arc PR. Also, from this property, we can easily know that any two angles that are inscribed in the same arc are equal. For example, if we have another angle as inscribed in the same arc PR, suppose we have another angle here, then we know that this angle must equal this angle here. Did you get it? Are you clear? Alright, then let's use what we have learned so far to solve some example questions. First, consider this question here. Given that triangle ABC is inscribed in the circle as shown here, angle A equals 70 degrees and arc AC equals 130 degrees. Can you find angle C? Any ideas? Okay. Arc AC is 130 degrees. That means if suppose this is the center of the circle, then this angle here is 130 degrees, right? So if you consider the arc AC, angle B is inscribed in arc AC, right? Therefore, we know this angle must be half of this central angle here. Or you could directly consider this as angle B is half of the arc AC. So that means angle B equals 1/2 times arc AC, which is half of 130 degrees, which gives us 65 degrees, right? If you know angle A, you know angle B, of course you can find angle C, which is 180 degrees minus angle A minus angle B, which is 180 degrees minus 70 degrees minus 65 degrees, right? Are you clear? Any questions? Alright, if no questions, let's consider another one. So suppose we have a diagram here. Can you find x given that angle APB equals 2x, angle ACD equals x, and arc BC equals x? Again, I'll give you 3 minutes to consider this problem, and then we'll have a look at the solution together, okay? Alright, have you finished? Let's have a look at the solution together. Okay, since angle B and angle C are inscribed in the same arc, which is AD, right? So they must be equal, since each equals half of the arc. Therefore, we know angle B equals angle C equals x, right? Also, since angle A is inscribed in arc BC here, we know that angle A must be half of that arc, which is 1/2 of arc BC, right? Which equals half of x. So that means we have solved A in terms of x, we have solved B in terms of x, we also know this angle is 2x. Therefore, we have the sum of the three angles AB and APB must equal 180 degrees, right? Therefore, we know angle A is half of x, angle B is x, and angle APB is 2x. Then we have equation in terms of x. This solves x equals 360 over 7 degrees, right? Alright, then let's consider one last question. Chords AC and BD of a circle meet at point P as shown on the right, given AP equals PB. Can you show that AB is parallel to CD? It seems like they are parallel, right? But can you prove this? Okay, have you finished? Okay, first of all, since AP equals PB, we have angle PBA equals angle PAB, right? This angle equals this angle in that isosceles triangles. And if you consider the arc BC here, then this angle should equal this angle, right? Because angle CAB and angle CDB are inscribed in the same arc BC. So we have angle CDB equals angle CAB, right? Therefore, we know angle CDB equals CAB equals angle PBA, right? So if this angle equals this angle here, then we know AB must be parallel to CD, right? Okay, again, let's make a summary here. This is the most important property we have learned so far. The measure of an inscribed angle is 1/2 the measure of the arc it intercepts. Also, from this property, we obviously have the second property here. Any two angles that are inscribed in the same arc are also equal, right? Okay, so if you don't have any questions, let's call it off for today. Remember to complete the homework and submit them to Google Classroom before the deadline. Okay, I'll see you next time.